All seen it, right? Stunning photorealistic images, incredibly realistic audio, all thanks to generative AI. It's amazing stuff.
Absolutely incredible.
But there's this side effect we don't talk about much, the enormous energy bill that comes with it. So today, we're diving deep into, well, a pretty bold vision for a sustainable digital future.
Yeah, that's exactly our mission for this deep dive. We're looking at how some really cutting-edge AI diffusion models, specifically, and this revolutionary hardware called SPI memory, are coming together.
Good.
And they're tackling this huge energy challenge head-on. The goal isn't just greener AI, it's really about unlocking new ways of computing, making it genuinely accessible, affordable, and scalable for you globally.
Okay, so let's maybe unpack the scale of this energy problem first. Because deep learning, the computations involved, they increased something like 300,000 times just between 2012 and 2018.
Yeah, a 300,000-fold increase. It's staggering.
It really is. And that leads directly to a surprisingly large carbon footprint. You mentioned data centers globally, they're already using about 2–3% of all electricity.
Right, which is a huge number on its own.
A huge number. But is this mainly an AI thing, or are there other big digital energy hogs out there?
That's a great question because, connecting this to the bigger picture, it's definitely not just AI. Think about proof-of-work blockchains.
Like Bitcoin.
Exactly. Bitcoin alone can chew through 100, maybe 200 terawatt hours a year.
Wow.
To put that in perspective, that's like the energy use of a small country.
Okay, that's massive.
It really raises the question, how do we get all this amazing AI and digital infrastructure without, well, costing the Earth quite so much?
That's the core challenge. So where do solutions start? You mentioned diffusion models. These are a type of generative AI, right? They create new data by kind of simulating, adding noise, and then taking it away.
That's the basic idea, yes. And they've achieved really state-of-the-art results in things like image generation, video, audio.
So what makes them promising for energy efficiency?
Well, what's fascinating is how they've sort of naturally evolved towards being more efficient. Specifically, there's a type called latent diffusion models, LDM.
Okay, LDA.
They work in a compressed latent space. Think of it like an architect using a super optimized blueprint instead of a giant full-scale model on site.
Got it. More compact.
Exactly. And that drastically cuts down the computing power and the memory needed. We have some pretty compelling data here. Older models often needed, say, 1,000 steps or more to get a good output.
Right.
LDMs can often do it in just 20 to 50 steps.
Huge difference.
Huge. And memory usage, cut by maybe 10 to 100 times. The energy for generating one image, inference energy, has dropped from joules down to millijoules on the right hardware.
Millijoules per image. That's incredibly efficient on the software side. Is that kind of optimization happening across all generative AI tasks, though? Or are some still really demanding?
That's a fair point. While the gains are significant, the core ideas, like working in that latent space, apply pretty broadly. And there are other tricks, too, like faster ways to do sampling, conditional generation. It all adds up.
Okay, so software is getting much smarter, much leaner. What about the hardware side? You mentioned spin memory earlier. Is that the other piece of the puzzle?
Absolutely. It's a potential game changer on the hardware front. Spin memory, or spintronics, uses the spin of electrons to store data.
Okay, electron spin.
Yeah, and the key benefits are non-volatility. It holds data with no power, plus it's fast, really durable, and crucially uses ultra-low amounts of energy.
And the specs, what kind of numbers are we talking?
Oh, they're seriously impressive. We're talking switching energies below 1 femtojoule per bit.
Femtojoule. That sounds tiny.
It is. Like a single AA battery could power trillions of these operations. Endurance is over 10 to the 12 write cycles, way beyond normal flash memory. And prototypes are showing on-chip bandwidth over a terabyte per second. And maybe the biggest thing is monolithic integration. Imagine putting the CPU, the GPU, and this SPN memory all together on one single piece of silicon.
So everything's close together, less moving data around.
Precisely. Moving data takes energy. This minimizes that waste.
Okay, so let's bring it all together. We have these efficient diffusion models on the software side and super efficient SISP and memory on the hardware side. How does this convergence create that
AI could potentially guide the mining process to skip ranges of computation that are unlikely to work.
Okay.
That could cut the energy per block by maybe 10x, even 100x. It also opens up ideas like proof of useful work, where the computation actually does something beneficial besides just securing the chain.
Interesting.
And putting SPI memory in the blockchain nodes themselves could cut their idle power use by over 90%.
Okay, so big savings potential there.
Yeah.
What about AI itself, like artificial general intelligence or supercomputing?
Right. Here we could see things like persistent instant-on AI models because the memory doesn't need constant power. And in-memory compute, doing the calculations right where the data is stored in the speed memory.
Less data shuffling again.
Exactly. That could reduce training energy maybe 5 to 10 times. And the energy for running complex models, the inference, could drop below 1 millijoule even for really tough tasks.
And data centers overall.
The collective impact could be huge. Spin memory alone might cut the energy used just for memory by 50–80%. Add AI-optimized scheduling for workloads, and you could potentially reduce total data center energy by 10–30%.
So it really is about drastically slashing the energy cost per sort of digital action, whether it's AI, blockchain, or just general computing. It feels like it could genuinely make massive planet-scale digital services affordable and feasible.
Ultimately, this convergence isn't just about making tech faster or slightly greener. It's about fundamentally redefining computation itself, making it sustainable, making it accessible to everyone.
It leads to a pretty profound thought, doesn't it? If knowledge, as they say, is valuable when it's understood and applied, what happens when computing power becomes almost limitless and incredibly energy efficient? What new kinds of useful work, as you put it, might emerge? How could that change how you, the listener, might tackle huge challenges like climate change or push the boundaries of scientific discovery? Something to think about.